In the last video, we asked a question about a fly that was living at the origin in R3, and we were asking, can that fly get to a particular point in R3 if it was only allowed to fly in sort of directions or scalar multiples of certain vectors? So those vectors were 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1. And what we discovered is that the fly could get to the point in the original question as well as any other point in R3. And actually, we only needed to go in directions or scalar multiples of v1, v2, and v3. So we didn't even need v4 in order to do this. Sort of in linear algebra terms, the question we're really asking is, does this set span all of R3? So does the set of vectors v1, v2, v3, v4 span R3? And not only could we say, yes to that question, but we could do even better. Again, we don't even need v4. We can get to any vector we want or any point we want, depending on how we're viewing things, using just multiples of v1, v2, and v3. So it turns out that the span of just, v1, v2, v3 was equal to all of R3. It's not too hard to see that, right? If I wanted to get to the point X, Y, Z, let's say in R3, I could just multiply V1 by X, V2 by Y, and V3 by Z, and I would get precisely to the point where I'd be, dealing with the vector xyz, and it would be pointing at, in its standard position, the point, xyz. So it's not too hard to see that. It's not too hard, hopefully, to see that we do not need v4 to span all of R3. The sort of key here is that we have, in the case of all four of these vectors, enough vectors to span all of R3. But if we drop v4 and we can still do it, it's because v4 itself can be written as a linear combination of v1, v2, and v3. And so, and it's again kind of easy to see how to do that. V4 just equals v1 plus v2 plus v3. So this tells us, v4 is a linear combination of v1, v2, and v3. So that means that the original set, v1, v2, v3, v4, is linearly dependent. So the question about, can we get to any point is a question of spanning, but the question of, how many vectors do we need? Do we have too many vectors here? Could we potentially get rid of these and get rid of, one or more of these and still span all of R3 is a question of linear dependence. If we, dropped two of those vectors, so we're just considering v1 and v2, now we cannot get to every point in R3. We're sort of stuck in this case on just the xy plane. We can't get any of those z coordinates. And so, kind of again, in linear algebra terms, we would say that the span of v1, v2 does not equal R3. So although we have linear independence here, we don't have spanning. So we're kind of asking questions of, can we get to every point? Do the vectors we have span all of whatever space, in this case of R3? And are we doing it in the most efficient way? Do we have too many vectors? So, kind of these questions of, do we have enough vectors? That's sort of a question of, do the vectors we have span the space that we're interested in, getting to? And then the other question might be, do we have too many vectors? Are we sort of doing this in an efficient way? And this is a question of, linear dependence, or maybe I'll say independence. Because if we have the sort of, if we don't have too many, then the set we are dealing with is, most likely linearly independent. So kind of putting these two questions together, making sure we have enough to span the space, but not having too many where we're doing this kind of in the most efficient way, are questions of spanning and linear independence. And if we do answer both of these questions, like we have enough and we don't have too many, then what we are dealing with is what's called a basis for our set. So let's go ahead and define that. We say that a set of vectors v1, v2 up through vn is a basis in Rm, is called a basis for Rm if the set of vectors spans Rm and the set of vectors is linearly independent. So you see those two ideas here, spanning and linear independence. And those are going to be the two key ideas. And again, kind of going back to that example we were looking at a minute ago, the question of spanning is making sure we have enough vectors. And the question of linear independence is a question of making sure we do not have too many vectors. So we're looking for just the right amount. So let's take a look at some examples here. Let's say we have these two vectors in R2, and we want to know if they are a basis for R2. So we want to know, so is this set a basis for R2? So we want to know, are these, is this set of vectors linearly independent, and does this set of vectors span all of R2? We can check for really both of those things, but let's just consider checking for linear independence here by considering the matrix whose columns are given by those vectors. And in general, we might, get this into reduced row echelon form through row operations. This given matrix already is in reduced row echelon form, and we can identify where the pivots are. We just have the one pivot here. And so, we can see that the second column here does not have a pivot. And so no pivot in the second column, which is an indication that these vectors are not linearly independent. And on sort of further inspection, you can pretty clearly see that the second vector, maybe we call these v1 and v2, you can pretty clearly see that v2 is just a multiple of v1. And so these are not going to be linearly independent, so this is not a basis. These are also not going to span all of R2. We could see that the second row, I should say, does not have a pivot, and so these will not span R2 either. But we're kind of checking for linear independence first. So not a basis. We cannot get to every vector in R2. This doesn't span, and these are also not linearly independent. And what about this example, 1, 0, 0, 1? Again, we could consider putting this into a matrix. And now we see this is also already in reduced row echelon form. We've got our two pivots. We've got a pivot in each row, a pivot in each column. So we have both, spanning and linear independence. And so this is a basis. So this set spans R2 and is linearly independent. So the set is a basis for R2. So we can get to any vector we want in R2 by, it spans, but also these vectors are linearly independent. So we have the right number, we have enough to span, and we don't have too many where we have linear dependence. Let's take a look at this example. So we sort of have tacked on an additional vector to what we had earlier, 1, 1, and this is no longer linearly linearly independent. If we called this one V3 and this one V1 and V2, we could see that V3 equals V1 plus V2. So this set is not linearly independent, and so it's not a basis for R2. Okay. It spans all of R2, but it is not a basis because they are not linearly independent. We sort of have too many vectors here. We can get rid of one, namely if we get rid of 1, 1, right? Now we're back to the previous situation. Let's take a look at an example for R3. We've got 1, 0, 0, 0, 1, 0, 0, 0, 1. We're sort of back to that original fly example where we sort of discovered these three vectors would span all of R3 and are also linearly independent. So this is a basis. This set is a basis for R3. We have both linear independence and spanning. What about this example? These three vectors are not going to, if we were to consider this matrix here, okay, this is almost in reducer echelon form, or no, this is in reducer echelon form, right? So we could see our pivots here and here, and we can see that not only will we not get spanning because we don't have a pivot in every row, right? Our third row does not have a pivot. We also don't have linear independence. Our third column does not have a pivot, so not a basis here. Okay, so it's not just the number we're looking for. This set was a basis. It had three vectors. It had, sort of enough vectors to span and not too many to be, to still be linearly independent. Here we had three vectors, but, a different choice of three vectors, and we no longer have spanning or linear independence. So if that number three is maybe a magic number, we still have to be sort of careful with which vectors we're actually choosing. Take a look at what's called the standard basis, in this case for R2. We introduced this notation earlier, these sort of standard basis vectors, we might call them, for R2, E1, which is 1, 0, and E2, which is 0, 1. This set of vectors, E1, E2, is a basis for R2. And we sometimes call this the standard basis for R2. Here would be the standard basis for R3. And then more generally, if we have the vectors E1 through En of this form, E1 is, the vector with a 1 in the first position and 0 is elsewhere. E2 is a 1 in the second position and 0 is elsewhere, and so on and so forth. This would make up our standard basis for Rn. And just sort of reiterating, the set E1 through En is called the standard basis for Rn. Not too hard to show that this set is both linearly independent as well as would span all of Rn. But I will point out here that there are infinitely many sets that span all of Rn. So there's not necessarily anything super special about this particular basis I was saying infinitely many sets that span all of Rn and are linearly independent. Would form a basis. So there are infinitely many, maybe I'll put that down here. So there's infinitely many bases for Rn. I don't want us to get sort of caught up in, oh, this is the basis. This is maybe what we'd call the standard basis, but there are many, many choices. So anytime you've got a set of vectors that span Rn and are linearly independent, they will form a basis. Now, we are going to talk about something that all of these bases will share, namely the number of vectors in them. So a little preview of something to come in a future video, but the actual makeup of these bases could be very different.